So Euler's method for differential equations is basically an approximation technique that allows us to solve a differential equation. So in some ways it's similar to slope fields, and it does lend itself to slope fields as well, because with slope fields we were approximating the solution by just kind of following slope lines. So it is actually fairly similar to that. This is more of a numerical technique though, and basically we're going to solve these differential equations. It's typically when we have the derivative in terms of x and y. And the process essentially is this. We're just going to generate short line segments, and hopefully we're going to approximate the function. So the way this works is we're going to use a linear approximation. So we need the linear approximation formula. So here is the linear approximation formula in point slope form. So our derivative gives us our slope. Okay, we have a starting point x naught, y naught, and we're going to try to get to x1, y1. Okay, so that's what we're going to do. So we're going to have some known point to start with, and we're going to generate an approximation point at x1, y1. So that's what happens here. We're just basically going to take the derivative at this point, which we can calculate since we have the differential equation. We have the coordinate as well, so we'll generate our linear approximation equation, and we're going to approximate the next point here. Okay. Now we can see that there is some error. There's going to be some error involved since it's a linear approximation to a curve. However, what we can do is just kind of keep doing this. So we're going to take one point here, okay, and then starting at that point, we're going to take the slope at that point, because again, we have the differential equation to calculate the slope at this point. We have the coordinates, so we can come up with the linear equation, and then we can generate a second approximation here. And then we repeat the process. We find the derivative at this point because we have the x and y. We find the linear equation because we have the slope in the x and y. And then we extrapolate that to find the third point. And we can keep repeating this process. And what we're going to end up doing is we're going to kind of trace out a map of this function. So it's not going to be exact, but it's going to tend to follow it. Okay? And so the process is going to be this. So I'll list out the process here. The first step is we generate the slope. We find slope, okay, with the function dy dx. Okay. The next step is to generate the linear approximation formula. Okay, and the third, what we're going to do with that linear approximation is then we're going to estimate the next point. Okay, so once we get to, we're going to start here. Okay, we're going to make a linear approximation to get to here. Okay, and then once we get to this point, we're just going to repeat the process so that we can jump to another point, and then we're going to repeat the process. So once you get to this point, we repeat. Okay, and we're just going to keep repeating for as long as we need. So this process again is, if you kind of notice, this is just kind of, we're attaching slope segments together, which kind of lends itself towards, so it's very similar to, so I'm going to maybe say this is similar to slope fields. Okay, and the slope fields are useful for us in the same way. And you're going to see that we're actually going to use these with slope fields as well.